Hey everyone, back to a new awesome video, and today we're going to continue with our series about classical mechanics. Today we're going to start with energy, and in these first two videos about energy we will treat kinetic energy and work. Today specifically we're going to introduce kinetic energy, then we will introduce also work, and finally we will understand the integral formulation for work that will lead us to the work-kinetic energy theorem. So let's start! Great, let's introduce the first quantity of energy we are going to talk about, kinetic energy. Kinetic energy is the energy that an object has because of being in movement. Therefore, it's going to depend on the velocity, and it's going to also depend on the mass of the object, because it's not the same thing. It's a kind of a obvious thing that a very big object, a very massive object, is going to have a lot more energy than a small object. Therefore, kinetic energy is defined to be equal to 1/2 of the mass times the velocity square. We will see when we introduce work and the kinetic energy work theorem, we will see why this definition is pretty nice. Usually, we will be interested in the variation of kinetic energy because in a moving frame, in another inertial reference frame, your kinetic energy can be different. Therefore, we are usually interested in the change. The change of kinetic energy is no other thing than 1/2 times the mass, because the mass is going to stay the same, and you have the velocity at t final minus the velocity at t initial, both of them squared. This could also be represented as 1/2 times mass times the variation of b squared. It's important to differentiate between b squared, the variation of b squared, and the variation of b squared, because they are not the same thing. Also, note that kinetic energy is a scalar quantity, because velocity is a vector. However, the square of a vector, or the scalar product of a vector with itself, is just a scalar. Another important thing to note about kinetic energy is its units. We can see from this equation that it has units of mass, that is kilograms, times meters per second square. In the SI units, this is also known as a joule. And these are the units that we will use most of our time in classical mechanics. Another important thing to note about kinetic energy is that it has another formulation. Recall our definition of momentum. It was mass times velocity. Therefore, kinetic energy is sometimes expressed, and this is mainly done in quantum physics or in particles physics, such as p squared over 2m. Which you can see it's really the exact same thing, because we are just taking another m and we need to have one in the denominator for it to work out. And this is the most important facts you need to know up to now about kinetic energy. Great, now let's introduce work. Imagine you have an object sitting on this floor and you apply a force to it. It is not the same thing to apply a force to the object, force F, to the object and move it just a couple centimeters, to move it a lot of distance. Therefore, we define work as the scalar product of the force with the distance that the object moves. We can see from this definition, and it is not the complete definition we're going to have, but it is kind of a primitive definition. We can see that the only force that matters is the one that is employed in moving the object. If you do not move the object, such as me holding this pen, I'm not doing work. But if I start moving it upwards, then I'm doing some work. And if I start moving it in that direction, I'm doing some work. And once again, if I do it like this, I move the pen like this, I'm doing some work, but because of the force, I'm doing it that direction, not because of the force that I'm doing to hold the pen from not falling down. Alright, so this is a definition of work we usually have when we are studying, and we might add the formula for the scalar product, and we usually do F, the magnitude of F times delta X, times the cosine of the angle they form. And this will be very useful if our force isn't changing. However, imagine that we first do a little bit of force and move it a couple centimeters. That will do a work of F1 delta 1. Then we do a little bit more of work and move it a little bit more of distance. Therefore, that's the next year, we'll have some more work. And we do this small by small in small amounts. Let's say for a small x1, for a small x2. If you realize we're going to have an infinite sum, and in the limit in which our force is continuously changing, the correct definition of work will be the integral of our force dotted with the change in position of our object. And this will be the definition for work that we are going to use most often. Another important thing to note about this work is its units. We can see from here the units of work are newtons times meter. And if we expand our definition of newtons, we see this is kilograms times the units of acceleration, which is meters per second square times meters. And this is kilograms meters square times second square. And if you remember from the last segment, this is no other thing than joules. That means that the units of work are the same thing that the units of kinetic energy. And in the next segment, we will see how these two are related. Alright, let's try to find that relation. If we have our work, the work we have made from an instant A from a place A to a place B, because we are integrating over space, we define it in this way. And we can see that A to B of that is no other thing than mass times acceleration. This is pretty straightforward. Now, if we expand this acceleration in terms of velocity as a differential, we find this is this. So everything is pretty straightforward. And now this is the key step. If we change this dt to the velocity, and therefore we change the thing we are integrating with respect to, in fact, to do this mathematically correct, we will have to do it first with the differential of work and then integrate the differential of work, but it will work anyways. We have that this is the integral from b at a to b at b of m dB times dr dt. That is no other thing than the velocity. Therefore, we can carry out this integral and we find it is 1/2 mb squared from BA to BB, which is no other thing than 1/2 m times the variation of b squared. And we see this is the change in kinetic energy. Therefore, we have found that kinetic energy is defined in a precise way such that work equals the variation in kinetic energy. And this is the work-kinetic energy theorem. That is all for today. I hope you understood all of these concepts about energy and kinetic energy that in general are very difficult to grasp because energy is something very non-tangible. However, it is a very important quantity in physics and it will help us in lots of problems. So it's very important to understand it correctly and try to get an intuition about how it works. Any doubts left, you may ask them in the comment section. I'll try to answer them in the best way I can. I hope you liked it and remember to like the video if it was the case, subscribe to the channel, press the bell and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome!